My name is Mackenzie Maxwell, and this is my Lab 2 motion of a falling object. The goal of this lab was to observe an object in freefall motion, analyze the effective drag on the final velocity of the object when the object reaches the ground, compare velocity versus time graphs between all three simulations, and compare the significance of terminal velocity. I recorded a crocheted octopus falling to the ground and analyzed with tracker. I then created two simulations in Python, one regarding drag force and two excluding drag force. This lab explored the effects of Newton's second law, whereas F equals ma. According to the results of this lab, Newton's second law, where F equals ma and where a equals negative 9.8, only applies to objects in freefall motion without any kind of friction. Because the simulation occurred in the real world, the tracker model differed from the glow script model that only took into account gravitational force. These are the scientific principles of this lab, whereas we have Newton's second law, the velocity update formula, the position update formula, gravitational force, drag force, and net force. As you can see in the diagram to the left, the octopus has a force of drag, which is in the opposite direction of motion, which is f of g. These are the results of the tracker model. There's a scaling factor of the wooden dorm desk, which is around 0.6 meters tall. The object was the octopus, which was 0.02 kilograms. The axis, which were the initial position of the octopus, which is 0.6 above the horizontal. The system was the octopus, and the surroundings included myself, the earth, and everything around the octopus. The initial position was 0.6 on the y, the initial velocity was 0, and the duration of motion from when the octopus was released and hit the ground was 0.37 seconds, and the final velocity is as follows below. As you can see, the position versus time graph has a curvature indicating acceleration, and the velocity versus time graph has a downward slope, meaning it has a negative acceleration. This is the coding for the Python model taking into account only gravitational force. As you can see, B equals 0, meaning there is zero drag acting on the system. I included the initial position, the initial velocity, and the duration of the trial. As you can see in the table below, the duration of motion from when the octopus was released and hit the ground is much lower than what was observed in the tracker model, and the velocity was also much steeper. This is the Python model that included drag within its calculations. The initial position, the initial velocity, and the duration of the trial remain unchanged from the previous Python model. I calculated drag, which was 0.012. It's a constant. I then plugged in this number to the equations below to calculate for net force. Net force is F of g plus F of d. F of g is the mass of the ball times the gravitational force, and F of d is the equation as follows. As you can see, the duration of motion is much closer as, or even approximately the same as the tracker model, as well as the final velocity is much closer to that of the final velocity of the tracker model. As you can see, these are the three graphical representations of each through trial. On the top left, we have the tracker model. On the top right, we have the Python model that took into account drag. And on the bottom right, we have the Python model that did not take into account drag. This lab was all about Newton's second law, which describes the acceleration of an object based on the total force applied on the mass of the object. This is commonly written as F equals ma. The more downward force, the faster it will accelerate. However, if there is an upward force, such as air resistance, the object will accelerate towards the ground much slower. This means that the simple equation F equals ma is a little more complicated when operating in the real world, as you have to take into account frictional forces such as drag or air resistance. In this case, the force of drag was observed, making the downward acceleration slower than that of the ideal world scenario. As you can see from the table below, the final velocities differ a bit. The tracker model and the glow script model that took into account drag have very similar negative velocities since they are falling to the ground. And the glow script final velocity was much higher since it had a higher acceleration, because it didn't have a frictional force acting against it, it was able to reach that final velocity a lot quicker than the tracker model or the glow script model that took into account drag. Possible sources of error: human error, since the object was moving somewhat fast towards the ground, tracking data points could have been a little off. The measuring the mass of the object could have been a little off as well, since I didn't have access to a scale, and also measuring the height of the desktop could have been a little off as well, since I didn't have access to a meter stick. Finally, we have the discussion questions. The computational model that includes f of drag would most accurately predict terminal velocity. Without drag, an object in freefall motion would essentially accelerate forever, but because of drag, there is a point where a velocity higher in magnitude cannot be reached. Graphically, the more so nonlinear nature of the velocity versus time graph of the glow-script model that includes drag indicates that a change in velocity or acceleration eventually flattens out to a constant velocity, indicating terminal velocity. The terminal velocity is a velocity value that remains constant for all objects under all circumstances. While an object may reach terminal velocity faster if it is thrown downward, the terminal velocity would not differ from that if the object was simply dropped. It would just take longer for it to reach the terminal velocity. Thank you so much for watching.